x0 equal to 1/4, there does not exist any free smooth such that I have u minus v as a strict max at 1/4. Because there's no way to slip inside this thing, this function. But I can always put something above it. I can always touch it freely. So, but of course there exists a lot of free smooth such that u minus v has a strict has a max at 1/4. I can always touch it a lot like function above. And you see, what is the slope of this guy? The slope of this guy gonna be staying between this guy and this guy, right? The slope is between these two slopes, any slope in the between is fine. I can put any plane, any slope in the between, right? So what does that mean? That means that I have phi prime at 1/4 is always stay between -1 and 1. Right? It's always between this -1 slope and +1 slope. Okay? Now, u minus v has a max at this point, so this is the test of viscosity subsolution. I need to have this inequality also. So I need to have phi prime of 1/4 is less than or equals to 1. Is that correct? It is correct, right? Because between -1 and 1, so this is correct. Now, another point I need to check is that at x0 equal to 3/4. I need to check because this was a breakdown. Okay? I need to check. Now, this is a reverse picture. I cannot touch this from above. There's no such function that can sort of move this way. But I can touch this from below. So, this is a picture. This is a two slope. I can always touch it from below. Anything from below like this is fine. Okay. So, I'm not going to write out that. So, there exists a lot of phi such that I have u minus phi as a strict mean at 3/4. Just any of the blue guy, right? And then also the slope must be between -1 and 1, right? So I also have phi prime of 3/4 must be between -1 and 1. Now, this has a strict mean, so I need to go to the second definition where it has a strict mean, right? So I must have, we must have phi prime of 3/4 always greater than or equal to 1, which is of course the contradiction, right? Because the slope here can be less than 1. But we are requiring the slope has to be greater than or equal to 1, so this is a contradiction. This is moved by B style. So I learned from my advisor that this is the only useful notion of moved by B. That's what I learned. But anyway. Is it correct that this is also the notion of moved by B school, meaning that it's very hard? Sort of zigzags that is very hard. I don't know. Anyway, so you see, so that means the yellow guy over there is not a viscosity solution. So can you tell me, can you guess? Can you give me a viscosity solution of that equation? What? Okay. Yeah. So you are allowed to go up and turn down, but you're not allowed to go down and turn up. Right? Whenever you go down and turn up, you're gonna end up in some trouble. So actually, here okay, we can guess that the viscosity solution is this one. Is the viscosity solution. What do I mean by that? It's the only one. It's the unique one. Whenever you go down, you turn up, you're going to end up in trouble. So you have to go up. You're only allowed to turn down once. It's the viscosity solution. It's the only one. Yes? Yeah.
The problem with stationary equation is that I could put it with minus h instead of h, and so you have this understatement that the time derivative was somewhere in the equation at the beginning and not.
Sorry.
Ambiguity, because otherwise, I mean, this one should be as well.
Yeah. Okay. So this is an equation without time. So I'm going back and forth without time and time. So it's, that's a good point. This is stationary problem. I'm going to mention your question now. That is kind of tricky. That this is the viscosity solution, and it's the unique one. And then and in general, I'm going to give you in general. You can go back home and test this one for fun. If we look at this problem, du epsilon, du x equal to 1 in any domain u, and you have u is equal to 0 on the boundary, then the viscosity solution, the unit viscosity solution is u equal to the distance function to the boundary. You can go back home and check this. This is pretty fun. From x to the boundary. Okay, assume that the boundary is maxing out. Okay, now let's go to that question. Now, how about, this is a very weird thing. How about minus du u equal to 0 on the boundary. So we're going to look at the minus equation, right? Minus h, minus this. It's crazy that in this case, this is not a viscosity solution anymore. Minus 1. So if we put the minus higher, viscosity solution, because despite the max and min thing, if you switch, it's completely switched. So then, let me put b here. Then the unit viscosity solution now is not this one, it's minus sign. So in other words, if you have u is a viscosity solution, it doesn't mean minus u is a viscosity solution. You have to be very careful. Very careful. We have to put the minus sign. Okay, it's kind of tricky. Okay, I thought it's good. Let me check. Any questions so far? Okay, so so let me mention another definition of viscosity solution, and then I'm going to do the Kendall-Leon's proof of units. Yes, questions? Okay, you can ask me if you don't miss if you want, and you feel shy. Okay, so another definition, another equivalent definition of 1 and 2 above. So I can put one term here is that instead of saying that I have a strict maximum, that means in the picture above, u minus phi has a strict maximum, means that u is being touched by phi from above, and then this is the gradient. This is the gradient of phi. So I'm not going to describe clearly, but if we have p and s is in the super gradient. B plus super gradient means it's above. B plus u x 0 t 0 is going to be s plus h x 0 t. So p is basically d phi and s is phi t. And then 2 prime equivalent with 2 is that if p and s is in the subgradient. D minus U x0 t0. You have S plus H x0 t0. So subgradient means that we have things, have planes stay below. Okay. Just take it. Okay. So now Crandall, I'm going to do Crandall-Lyons curve of uniqueness of viscosity. So from the advanced derivation that we do viscosity approximation, we pass the limit, we use as always some soft analysis, we have some viscosity solution, a viscosity solution. Now, the big deal that Crandall and Lyons proved was that it's unique, right? It's one of the pattern of the theory of osmosis. Existence is there. Now we're going to do uniqueness and then stability follows quite easily. Okay. Well, what is the thing here? You have been saying that even, there are many solutions that sort of like this. So it's kind of like differentiable, but almost everywhere. It can be not differentiable at any point. And even the viscosity solution we test was basically like this. So it's not differentiable at one point. So there's no way to have differentiable solutions for Hamilton equation. Up to now, I'm going to address that. Up to now, most of the time, you only have viscosity solution is ellipsis in general. It's never single in general. Ellipsis. So the problem is that when it's ellipsis and you have things not differentiable, you cannot really prove uniqueness easily. So let me state the theorem. So theorem, assume that U and U theorem are bounded and continuous and uniform or whatever, and continuous in Rn cross 0 infinity. Okay, at the end of the assumption that it's bounded. It's not, it doesn't matter. I'm going to do that later. The bounded is